I'll start recording. So what we're covering today is milestone 4 and parallel programming. Milestone 4 traveling courier problem, which should already be taught in lecture. You're given a number of depots. Some of them are pickups, some of them are drop-offs. You must be picking up and dropping off in some order. And you will need to find the fastest delivery route. How should you do it? We can divide this problem into first, we need to estimate the travel time between all of the locations. The best way is to pre-compute this and store it. Then we can use whichever data structure you're storing that to find a good delivery ordering using some algorithms that are covered in lecture, or you can find them out using some research techniques. And then return the final tour. So you have the constraint of in less than 50 seconds. In this tutorial, we are only going to focus on the first part. Estimate the travel time between all locations and storing them. Your data structure will look like something like a matrix where you can access the time using the from and to intersection IDs. The option 1, which is the fastest, is estimated by Euclidean distance. So you compute the distance, but this is inaccurate because it's not taking into consideration any of the path, any of the street, any of the speed limit, any of the turn penalties. Option 2, the exact path. It's accurate but slow. So what we are going to do, the slowest but the most intuitive way is to loop through all of the sources, all of the destinations, and find the path using A star. Assume we have K depot, pickup, drop-off intersections, and V total intersections. Can anyone tell me what's the complexity of this? So we are looping through all of the source and destination. So that's the pickup and drop-off intersections, the depots. And we have V total intersections. V cubed. Yeah, we have double for loop, but the double for loop is on the depots only. So double for loop is K squared. And then we times that with the A star complexity, which is the V log V. How do we further optimize for this? On large test cases, K squared may limit the time for your optimization, ordering optimization. So what we can do instead is instead of the double for loop, we only do a single for loop, but use the multi-target Dijkstra. Remember when we learned Dijkstra? The time it takes to find the path to a single destination is the same as finding the path to all of the destinations. So what is the complexity in this case? Anyone? kv log v, because we are removing one of the nested for loops. What if we want even more speed? Algorithm-wise, this is the fastest we can get using Dijkstra. Now we can look into parallel programming. This is just a graph to motivate everyone on using parallel programming. This magenta line is the number of transistors on chip each year. By Moore's law, the number of transistors on chip grows by each year, and this is true from this line. The single-threaded performance, it reaches a peak and then it starts dropping. It hits the threshold and it starts dropping. The frequency, the clock frequency, hits a threshold and it starts dropping by a bit. Typical power, which we don't want, keeps increasing, but it increases slower by later years. So the performance that we want to improve, incorporating the number of transistors, can only be achieved by increasing the number of cores. In modern CPUs, processors, we usually have more number of cores. This is an example of a 4-core processor. What the processor has, there are 4 cores. Each of them have its own set of resources, its own set of cache, and they all share the same shared memory. And that is the RAM. Each core executes its own instructions. All cores share a common memory space. In a single-threaded program, only core 0 is used, and it has the entire shared memory to its own. Most applications use one thread. Most of the applications you write use one thread, unless you specifically tell it to run multi-threading. You have been taught to write single-threaded applications, assuming there's no one else sharing the same memory with you. Because single-threaded applications do not need to worry about sharing memory. All other 3 cores are idle. If we add one more core, then we do need to worry about sharing the memory. If core 0 and core 1 are trying to write to one single variable at one time, there's no guarantee which one will win. So something will go wrong to at least one of the cores. And let's look into in the program's point of view. We have in your CPU the program counter, which points to somewhere in the instruction set in the memory. We have the stack pointer, which points to somewhere on the stack, also in the memory. This is the virtual memory space that your program assumes it's looking at. It starts at 0 here, and all Fs here. Instructions are always at the beginning. Then the global variables are allocated at the beginning. Then we have the heap variables, the new, which dynamically grows downwards. These are all of the variables that are allocated using new. At the end, we have the stack that starts at the largest address, which you should already know, and it grows upwards. That stores the local variables. In a single-threaded program, the program counter always points to the instructions. The stack pointer always points to its stack. When you add another core to it, you'll see that in the virtual memory space, it allocates another stack for the second core. Somehow that you don't need to worry about, but the stacks will not interfere with each other. So each of the cores have its own stack pointer that points to its own stack. Program counters are still pointing to the same instruction memory space. This means you may or may not be executing the same instructions. Thread 1 and thread 2. And all other memories, the global variables, the heap variables, are shared by all threads. And that's where you need to manage your memories. Each thread gets its own global variables. So just a summary of the basics. Each thread has its own program counter, so it can be executing a different function and is almost always executing a different instruction from other threads. Each thread has its own stack, so it has its own copy of local variables, not shared. Each thread sees the same global variables and the dynamically allocated memory. So that implies the threads can communicate through the memory in a very fast manner. You can write to a variable, another thread can read that variable and see whether it changed or anything like that. We can use the global variables or the dynamically allocated memory through pointers for fast communication. But you have to be careful that the threads are not conflicting in reads or writes to the same memory. And you can have more threads than the CPUs. The CPUs will divide its time. So it will give this chunk of time to one thread and it will context switch to another thread to execute the other threads. So some threads will need to wait for other threads to finish if there are resources being shared. Is this good? These are the multi-threading libraries you may use in Milestone 4. When your program starts to execute in the main function, it creates the first thread, which is the main thread. If you need to create more, you have two options. The first option is the OpenMP compiler directives. This is what we recommend you to use in M4 because it's very easy to write. It is higher level code. It will compile and run serially if the compiler doesn't support OpenMP, so you don't have to modify your normal code for that. And what it has is just this dash pragma OMP parallel for, and it will automatically divide the for loop into parallelly executing threads depending on the number of cores you have. If you want to have more control over it, you may use the C++11 threads library. And in this case, you will need to specify what each thread does. you will need to specify a different function that each thread executes based on what's specified in the thread library. And in this tutorial, we will only be showing OMP. Any questions before I? Okay. So if we want to parallelize a for loop with OpenMP, say we have a for loop that goes from 0 to 99, which is 100 iterations. We do some sort of addition. We can simply just add that line dash pragma OMP parallel for. And this, the compiler will directly divide this into 4 threads if you have 4 cores, 4 threads supported. And it will be dividing the ranges into 0 to 25, 25 to 50, 50 to 75, 75 to 100. And this is because the compiler knows that if we are executing memory operations in continuously in a sequence, it's faster than jumping. And when all of them finishes, it will start executing the following code. So this means the threads are joined back into one single main thread. Any questions before I go into the demo? Yeah.
Can you just say how many threads are being used?
In OMP, no.
You just take the max number of threads.
Yeah. The OpenMP web. So let's have a look at the CPP file. So basically what this does is it defines a vector length of 1000. It makes 3 vectors with vector length ABC. It initializes A and B. And then in the for loop that we are concerned of, we do something on C. We do this complex operation just to make sure it doesn't get optimized out by the compiler. So we do some computations on A and B and modify C. Let's first see what it does without parallelization. So it does all of the computations with number of threads 1 in this amount of time. Let's see how many cores we have on the UG machines. And we can do it using LS CPU. So here, CPU 16. We have in our Intel CPU, it has 8 cores, 2 threads per core. So these cores support hyper-threading. So we have 8 cores, physical cores, and we can run at most 16 threads. That's what it's telling us. So have the outputs here again. Let's enable parallel programming. Yeah, we enabled parallel 4. I'll make again. Do we have any hypothesis on what will happen?
Right. So number 4.
We're dividing by the number of cores, so are we expecting it to be faster or slower or?
Faster part.
Let's see then. 16 threads, but we are slowing down by a lot. That's weird, right? Just to show you whether it's because of this line. So not really. It's still slower, even if I'm not getting the number of threads. And that's because actually for a vector length of 1000, the gain that we get from multi-threading is not making up the overhead we're getting from making the threads, because making threads take time. So let's change the vector length to a larger number. We'll time it again, but I'll do the same thing. I'll comment out the parallel 4. Make. So that's the time it takes for single-threaded program. Then we are seeing a speed up there. That's compute the speed up. So it's 0.0628838 divided by 0.0082589.4. So that's about 7.6x speed up. But we have 16 number of threads. We are constrained at 7.6x because the dividers are shared across the 2 threads per core. So because of context switching, because of the limited resource, each core, we have to wait for one thread to finish in order to start the second thread. So the actual number of threads that we are executing in parallel are 8. So we are constrained by the 8 force. And just to verify this, let's do an even larger number. This out. On the same order of speed up. Is that good? So we have these speed ups and the problem size. For 1,000, we have a 0.25 speed up, so that's a 4 times slowdown. For 100,000, we have 0.868 speed up. And for larger problem sizes, we can speed up by 7.6x. And that will get closer and closer to 8. And that's because we have significant overhead to start the threads. So we need enough work to amortize this overhead. Do not parallelize if your problem size is small. Because parallelization can slow you down. So we always recommend you to write single-threaded program before trying to parallelize them. So converting a single-threaded program to use parallelization to use multiple threads. What you need to do is first include OMP. OpenMP is already linked and installed on the UG machines. So you just have to include OMP and then use the Pragma OMP parallel 4. This will automatically parallelize all of your for loops. A and B are global in terms of the parallel force. So these variables are shared by all threads. The i's are declared within the for loop, so they are local variables declared within the block. So these local variables are separate per thread. In this case, what will the program output be? So we're initializing vectors A to 50s, B to 2s. In the first parallel 4, we are adding AI with AI plus BI. In the second parallel 4, we are outputting. What do we hypothesize the program output to be? Let's keep this question in mind and let's do a typing speed contest. And I have 2 volunteers. So I have an external keyboard and the keyboard on my laptop. You don't have to know how to type. Use this. Me too. So one of you will use the external keyboard and you will type on line 1. One of you will use the laptop's keyboard and you will type on line 2. And the first to type that line, I am an amazing electrical and computer engineering student because I am a great typist and programming is mostly about typing speed. Please.
Guys, no laughing at the spelling.
Okay, who wants to get the external keyboard?
I can sit, right?
Yeah.
Oh.
Yeah. Okay.
So when you say line 2, what does that mean? I don't know what
Just look at the screen. And
Oh, my
there's
bad, my
line
bad.
one.
Which one am I? Line 1 or 2?
Okay.
Okay.
You can do 1 and you can do 2.
So we type at the same time.
You
sorry,
have to fight over the right to type.
What?
Yep.
Oh, this is like Safina, put her down.
Let's get ready.
When do we start? This is like,
Are you both ready?
no.
Wait, give me a second.
We're fighting?
It's like colonialism.
Yeah, you need to. You need to finish typing.
No,
first.
she is not me.
Hey,
Okay.
hey,
Wait, you're 1, I'm 2.
yeah. But we're fighting. I don't understand.
Wait, do you want us to just start?
3, 2, 1, start.
No! We're in the same line. One of you hand.
Don't use backspace. Don't use shadows.
Okay.
Get off! Get off!
There's too many.
Oh.
I'm waiting for you.
Oh my goodness.
Oh wait, what if I just? What the?
Are we actually going until this is done?
Is this how it's supposed to work?
Yeah.
What if I just write it for you?
So I'm not even.
Okay.
Yeah, okay.
Are we still going?
Oh my lord.
Yeah.
Yeah, tell me when you want to give up.
Yeah, I'm giving
Margaret, write this in.
I'm giving up. I'm giving up.
Okay.
So that was really good. I don't think
That was a very good demonstration.
It was a bad one?
Very good one.
And what can I say? It's in my blood. Okay, wait. I give up. Thank you for the opportunity, Sharon.
see how many lines we have.
Let's see.
This was great. Thank you. So who won?
Me. Everyone was. Yes. From what you just saw, that is what happens when two threads are trying to use the same resource. When two threads are trying to access the same resource at once. So when the for loop is trying to output the same line, it depends. You really don't know which thread can win when it's trying to output. So let's go to the BNC again. This is the same program as what I just showed you. The two for loops are both parallelized. And let's make thing, make. So from the outcome of the last typing contest, what do you hypothesize the output to be? It's beautiful. This is beautifully what we just saw in our typing contest. And this is because different threads are outputting to the same print at once. But we don't want that, because when one thread is printing, we want it to print finish printing that line before other threads come in. So this is why we need this command, pragma OMP critical. With this, we define the section inside the for loop to be the critical section. And this section will be enforced to be sequential, to be serialized. So if we do this, make, the output is still out of order, but we are seeing correct output.
I thought only change the line track.
This one?
Yeah, does that only affect this, like, you put code the latest, where it also.
This would I would say this affects the section below it, but you can check. I would say it affects everything inside this bracket. But you can try and see. And just to show that I'm not fooling you, I'll disable this parallel for. And we are outputting in order. Okay. Critical sections are for you to use in the cases where you will need to serialize from code. The pragma OMP parallel for does not check if parallelizing is safe or correct. So you'll have to check it and place the pragma OMP critical where needed. And this is for blocks. only one thread at a time can execute this block of code, this block of instruction. So the other threads will need to wait for this thread to finish before they start executing. So that might affect your speed. Because making everything critical will make your program back to serialized pace, and this will destroy your performance. Is everything good? If we combine the fast pathfinding algorithms with parallelization, these are the data we collected for n equals to 175, d equals to 20, and k equals to 370 interesting intersections. The baseline is the iterative A star that takes k squared v log v. Parallel iterative A star. So this is just parallelizing the A star will get 7.6x by parallelism. If we change iterative A star to multi-target, multi-destination Dijkstra, we can achieve algorithm speedup of 33x. And if we parallelize that, we can get 250x of gain. And that's algorithm plus parallelism. So the best way is to tune your algorithms before parallelizing, because the parallelizing gain is almost always fixed. So for your multi-destination Dijkstra, we are doing the sources in all of the key intersections. And we do find paths to all of the key intersections using multi-destination Dijkstra. So starts from source and it has all of the defaults as destinations. How to parallelize this code? We add a pragma OMP parallel 4 before the for loop. And inside the for loop, it's calling the find path. So everything inside the for loop is parallelized. Will this work? Anyone?
The size of the like, is there already a slot at index source?
Yes.
Yes.
Look at the global variables up there. Does it really work? So your wavefront, the nodes, the key intersections are all shared globals. And inside the find path, it's doing wavefront dot push. So it modifies the shared global variable. So when you are trying to parallelize this, you want each thread to have its own copy of wavefront. Does this make sense? So you move wavefront into local variables. privatized wavefront. So each thread is modifying its own private copy. It's not affecting any other threads. What about this variable? Key intersections. Can we keep it as global? Or should we privatize that?
Fine.
Yes, because we're just reading. It's fine. In the preload time matrix, when we're preloading, if the wavefront and the nodes are inside this matrix, so they are not actually global variables, is this okay to be left here? And why?
It's not in the bound path, so the threads will only be in the same, like, everything global for the threads.
It's global for the current scope. Yeah. It's declared here as local variables, but then it's passed by reference into find paths. So all threads will access the same location in memory by reference. So it's not okay. They are shared across all of the threads. So we still have to put them inside the local stages. Any questions before I move on to the demo? Okay. Both these. We'll go into the golden solution. Without modifying anything, let's run the ECE297 test. Okay. ECE297 exercise 4. Run tester. We do easy frontal. So easy Toronto tests for D is 25, D plus 2. N is 25, D is 2. And traveling Fourier take 0.77 seconds. Let's go into the code. So inside the find all paths multi-threading, let's comment out this parallel for. And compile again. So remember it's 0.77 seconds. Following period it took 5.0688 seconds. So that's how much parallelization gives you. From 5 seconds to 0.77. 0.77. Okay, next I'll be actually breaking the parallelization by making global variables. What I will be showing here is I will be explicitly putting in bugs. So I'll first define the first fat parallel global. This one. Let's see what it does. I put the pragma back. So after traveling Courier starts, we get a double free or corruption, and it aborted. Likely causes memory corruption, assertion failure, cannot parse tests. And generally how we fix this is we grab the debugger. So debug tester. Okay. The configuration, we set it to unit test debug, build target test libstreetmap, and launch target test libstreetmap. We build it again. You should already know how to grab the debugger by this time. Okay. And without setting a breakpoint, I'll just run the tester in the debugger and wait till it finishes. Okay, so it died in, see the call stop. It died in this thread. So we have multiple threads. We have these many threads, 16 threads, and the one that's paused on exception, that's scroll to the line that you know. It's on all nodes. And this all nodes is declared here. That is exactly the one variable that we are making global. And to make sure whether it is actually because of multi-threading, let's come here and disable multi-threading. I'll do release again. Don't have served. So it passes without multi-threading. And that's how you should be debugging multi-threading bugs. So first is to disable multi-threading to make sure whether it is because of multi-threading. In this case, it is, because disabling multi-threading makes it pass. Then, with multi-threading, we start the debugger and see where it failed. This again. And let's now put in another bug. So the prior bug is on the all nodes vector. Let's make the priority queue global and instead and see what's happening. What do we expect if we make the priority queue global? Will it segfault? Will it memory corruption? Will it just fail with a wrong answer? Let's see. There is some memory corruption, but your program won't know. It will return an illegal path. And you will get different answers each time, every time. Just in this case, we get illegal path. Path was empty. And that's because the priority queue should be private by each thread. Each thread is very dependent on the order everything is inside the priority queue. If some other threads are popping when it shouldn't be, you'll get this. And sometimes, in this case, it can go into something like infinite loop, because some threads are waiting for other threads to do the push and pops. So you'll get different things every time. Just make sure you are doing debugging in the same order as what I just said. Okay, we're just getting this today. Yep. Okay. Let's see. So our travel times will be stored in something like a matrix, where the rows are the from intersections, the columns are the to intersections. And we can store it in a vector of paths. And we can just fill it up from the results we got from the find paths. So we can access like this, like how you should be accessing a matrix from intersection 1 to intersection 2. If we write this like this, will it work? So we are returning a vector of paths from find paths, and we're directly pushing that back into the paths. Will this work? Especially in multi-threading. No?
Is my first back at the same time?
When it's pushing back, it will not push back in the same order. So if it's not pushing back in the same order, it will mess up with the IDs. Like what we're seeing in the print. It's not printing in the same order. It's not pushing back in the same order, so your from IDs are messed up. Yeah. It's misordering data, and reallocation or copying can occur in one thread while another is in the middle of a push, so it could corrupt your memory. So the correct way to do this is to resize your paths and then just write in with the correct ID. So every thread is guaranteed to write into separate memory, so there's no reallocation or interference between threads. Any questions? So generally, these are just general things you need to worry about when you're adding in multi-threading, especially for memories. When you're debugging parallel programs, the first thing is to disable parallelism and see if the problem disappears. If it disappears, then it's probably a race condition. Multiple threads are writing, reading a shared variable in the wrong way. Then when you identify that it is because of parallelism, re-enable it and run in debugger, especially if the program crashes. Run in debugger and wait for the program to crash, and you'll see where it crashes on which variable. And that variable is one variable that you'll most likely need to watch out for. Or if it's stuck in a infinite loop, run in debugger. When you see the infinite loop, pause and see where you are. To fix race conditions, the most convenient way is to privatize variables where you can. Making variables local variables ensures that each thread has its own copy. Or if there's no way of privatizing any variables and you need to ensure that it runs in the correct order or something, use OMP critical to force only one thread to read right at a time. Usually it costs performance, so we don't want you to use that, but if it's not avoidable, use OMP critical. Parallelization is limited. by Amdahl's law, suppose we have n cores and we have a fraction of parallelizable work. Not all work is parallelizable at a time. If you are trying to parallelize, say, half of your work, then the maximum number of speed up you can get is from this equation. So if you are parallelizing half of your work for 16 cores, you will probably get, this is half plus, even if your n gets to infinity, so this term cancels out, you can only get 2x speed up, at most, if you're only parallelizing half of your work. So that's what this is telling you. Your speed up will eventually thin out. What's the number of cores? And that's why we recommend you to optimize for your algorithms first and then try parallelizing, because you won't get as much gain as you want. Is this making sense? Yeah, improve your algorithm first, as what I just said. It's usually a bigger reward. Use the OpenMP pragmas because they are easy to disable and easy to add. Avoid modifying shared states, and this minimizes bugs. Prioritize so each thread has a copy for your critical variables. Always parallelize larger chunks of work. That will get you more reward. And you'll have runtime overhead for making threads. So also try to avoid that. If your work is not big enough, don't do it. Parallelization is hard. And yeah, experts get it wrong, and these are still open research questions in some research areas. So don't panic if you don't get it right. And for suggestions, that's the last slide. Get something simple working first, but in these 3 parts. Get a simple travel time estimate, simple ordering heuristic, return a legal solution first. And make sure you can pass some of the simpler test cases, and then try to use better cost estimations. And at the end, after you get everything working fine, parallelize only when everything is working well, if you want to get a further challenge. And yeah, that's it for today's tutorial. Any questions for me? Yeah. Any other questions? Yeah.
You have to do the ECE for
I think it's the same way.
so that there's no initialization.
It should be in your handout. If it says in,
Yeah.
maybe try it again.
So no.
If the, can you see the M4 header file? If it says there's no initialization, then probably you can just start writing.
Copy paste.
You are able to use your prior functions.
Yeah.
Yeah, and then you just need to write your own functions
still
on
things we
for
can find. That's why that will, the coder subpath function. The structure and the function that actually is called by the tester. Traveling courier.
Yeah, if you can see that function, and if you can include the M4 header, it's fine. Any other questions? If there's no questions, this is our last tutorial. And thank you for coming.